So I'm happy to introduce our speaker today, Dr. Xie Hu from Peking University. Xie's research is focused on using INSAR for examining landslides and subsidence across China, observing permafrost thaw in the Tibetan Plateau, and using machine learning to decipher various INSAR signals from different processes. So she completed her PhD at the Southern Methodist University in the US before spending some time at both Berkeley and the University of Houston before moving to Peking University, where she is currently at. So she'll be sharing some of her work today using SAR for diagnosing natural hazards to help for better mitigation and just understanding of these processes. So I'll hand over to you now. So whenever you're ready, feel free to go and start.
Yeah, thank you, Edna, for the introduction. It's my pleasure to give this presentation in this professional and SAR-oriented community. And today I'm going to update you about some recent progress made by my lab members, Yilin, Yuqi, Yongxuan, and Yuanzhuo. So they are all either PhD or master students. So we are going to focus on the SAR, how SAR can empower the diagnosis of acute and chronic natural hazards. So I believe our participants should have a very good understanding about synthetic Aperture Radar. Just a quick reminder that this tool can not only measure the displacement through the interferometry, but it can also reveal the land cover changes by utilizing the amplitude and coherence information that has been somehow underused by our community. And just to give you a thought, there are multiple forms of natural hazards, and most of them are associated with surface disturbance in forms of land displacement or land cover changes. For example, the landslide can denude the mountains and reshape the topography, while they can move at imperceptible rate or feel catastrophically, while the permafrost is thawing and sinking, especially in the present-day climate change, while the tectonics, perhaps the central focus of COMET Plus, includes the phenomena like earthquakes and volcanic eruptions, and definitely they relate to the ground deformation. Human activities like water pumping and oil gas extraction can also introduce localized deformation. Well, there seems to be an increasing number and more frequent extreme rainstorms, and vast areas can be swept by the floodwaters in a blink. But the coast regions somehow faced various types of climatic and geological hazards, and some areas are highly likely to be submerged under the seawater in decades. So can you imagine that the SAR can actually deal with them all? Now think about ourselves. To some extent, we all visit the doctors, and the doctors will ask about our symptoms and when they began and how they've progressed. So this information can help to diagnose if it's an acute illness, a chronic ones, or something between. Acute illness are characterized by the sudden onset, rapid progression, and immediate impacts, such as flu, heart attack, or pneumonia. While the subacute ones often lead to misdiagnosis, under-detection, or overtreatment, such as bacterial endocarditis. While the chronic ones often develop insidiously, progress over long periods with ambiguous onset, and most of them have multiple causes, such as diabetes and high blood pressure. Similarly, the natural hazards can be likened to the earth falling yield. Well, the floods and earthquakes are definitely the acute ones. Well, those thermokarst disasters occurred on the frozen ground, on the permafrost environment, belongs to the subacute ones. While slow-moving landslides and land subsidence can be considered as the chronic ones. So I'm going to showcase some studies and start with the acute ones. So here the typhoon Doxury made landfall in eastern coast of China and continues northward to Beijing metropolitan areas. It dumped a huge amount of rainwater and caused once-in-a-century flood in Hai River Basin, home to 160 million population. To mitigate the flood hazards, and there were 8 flood detention areas being activated. So here we synergize mountain source remote sense imagery from Copernicus Sentinel-1 and also China's domestic satellites like Galfan-3 and Lutan-1, as well as optical things from Copernicus Sentinel-2 to densify the temporal acquisition for us to recover the floodwater growth and the recession process that lasts for more than 2 months. So a quick reminder about how and why SAR can be so helpful in detect the water body. Because this system applied the side looking, when the electromagnetic wave interact with the water surface, is going to reflect it away, leaving very minimum returning to the sensors. So it left the water body in the dark black and can be easily retrieved just from the simple threshold approach. By comparing here the Sentinel-1 image collected before the event and Galfan-3 image collected during the flood event, we can clearly see the width of the water. The river has been widened clearly. Well, there are also some artifacts coming from the side-looking geometry. We can see the areas cast in shadows also present the darkness. So imagine that if we just use a simple threshold approach, the floodwater extent will be largely overestimated. So here we applied the deep learning approach by supplement the training model with the negative samples like the fish ponds or the hill shadows, and then fed into the deep Lab 3 is a classic semantic segmentation model to delineate the flood waters. So compared with the traditional threshold approach, deep learning can largely suppress the false positives in the hilly areas. And it can also be generalized for mountain source imageries with different polarization. And it can also recover the continuous shape of the floodwater due to the natural advantages of image segmentation. So our result shows the flood area larger than 15 square kilometers concentrated by the rivers, and flood area larger than 25 square kilometers concentrated around this 8 activated flood detention area. And these flood detention areas account for only 1% of the land area in Hai River Basin, but they hold 33% of the floodwaters. And later, we incorporate the SAR and remote sensing derived flood area with the digital elevation model to infer the flood depth. And our flood volume shows very good consistency with those derived from the hydrodynamic model. And then we can extract the footprints of the floodwaters. From upstream to the downstream, we can see those detention areas in upstream reach the flood peak in late July. When it's approaching to the midstream to the downstream, the arrival of the flood peaks arrives later, like in the early August or even the mid-August. Altogether, these 8 activated detention areas detain 2.7 billion cubic meters of floodwaters, while the Dongdian detention area alone detained about 1/3 of the total floodwater. Well, here we actually can recover the temporal evolution of flood depths on a pixel basis. So that can help us to assess how long did it take for the floodwater recession. Our results shows among these 8 activated detention areas, several drained within 2 weeks, and just one, the Dongdian detention area, drained in about 1 month. So here is another illustrative proof to show the effectiveness of the detention area. So let's see this green curve. That is the floodwater discharge in the downstream river. So that has been much dampened compared to the flood river discharge in the upstream, as denoted by the red and the blue lines. And that is because here the detention area really taken effective in reduced detained and retained the floodwaters. Okay, another type of abrupt natural hazard is earthquake. But our lab is primarily focused on the shallow process, so we are not investigating the mechanisms. Instead, we focus on the earthquake damage. And here's an example of magnitude 6 earthquake occurred between the Tibetan Plateau and the Lost Plateau of China in the end of 2023. The earthquake nucleated at a depth of 10 kilometers with a thrust faulting regime. So this event leads to widespread damage, including 13,000 landslides and liquefaction, as well as building damage. So here we synergize the geological and the environmental variables in the framework of classic machine learning method in order to quantitatively assess the co-seismic landslide susceptibility. Well, here the models also allow us to sort out the contribution from each contributing variables. And overall, we highlight 4 variables, that is PGA, peak ground acceleration, elevation, and slope, as well as damage proxy map, also known as the ground disturbance map, which is in essence from the differential coherence between the pairs collected before the event and spanning the event. So those color bars suggest the statistics for the landslides. Well, these gray lines show the statistics of the non-landslide pixels, and they show distinct disparities. And that's the reason why they can be so helpful for us to separate out those pixels and more importantly, to quantify the landslide susceptibility. Well, this event also induced a massive lateral spreading that caused tens of casualties from these 2 villages. So this is lateral spreading occurred on a gentle inclined slope and travels by 4.5 kilometers. So here, about 12 hours ahead of the earthquake nucleation, the Sentinel-2 satellite imaged area and shows an outstanding elevated soil moisture in the source area of the lateral spreading. So from the news report, we got to know there have been 3 days of continuous flood irrigation, which is a typical form of agricultural irrigation in the Lost Plateau of China during the winter time. So we believe this is a typical example of how human activities can somehow aggregate the earthquake damage. But similar phenomena has also been identified in the Palu earthquake in Indonesia several years ago. Here we also like to highlight and remind the importance of INSAR coherence and also amplitude products. Compare with the publicly available global data set of soil moisture and precipitation. INSAR coherence can really used as a replacement, and it can reduce and also refine the resolution by 2 orders of magnitude to just tens of meters. Okay, next is about subacute hazard that occurred on the permafrost environment. The permafrost is the frozen ground below 0 Celsius degree continuously for more than 2 years. It is characterized by the active layer in the shallow part beneath the organic layers, and it thaws and freezes in a regular seasonal pattern. The permafrost is widely distributed in the Qinghai Plateau, so we can see here denoted by the blue backgrounds. So permafrost also believed as the magnifying glass for climate change. So here's the map of a circular rate derived from Sentinel-1. So we can see at where the permafrost is distributed, we see mostly subsidence at 20 millimeter per year. It's also interesting to see the seasonal amplitude is so pronounced at the occurrence of the permafrost. Just within one single year, the surface elevation can change by 40 millimeter. Let's take a look at the seasonal variation. It represents the apparent frost heave and thaw subsidence from both the ascending and the descending tracks at selected targets. So here the gray lines shows the seasonal displacement with the long-term downward trend, while the blue line shows the ground temperature, and the red bars denote the time window with above 0 Celsius degree temperature. So we can see during this comparatively warm temperature period, the land going downward, that is thaw and subsides. So given the intrinsic physics, there are density changes between water and ice, so we can infer the active layer thickness using the seasonal displacement and also the volumetric water content. So here we can then derive the regional map of active layer thickness. So here we consider the volumetric water content in the thaw season from the soil moisture, and we resolved the volumetric water content in the dry and the freezing season through the in situ active layer thickness inversion, and after interpolating into the region map of volumetric water content. Okay, when the landslides occurred on the permafrost environment, it has a new name called retrogressive thaw slumps. And these are the videos we took in the field survey in 2023. So literally you can see the muddy flow and the head wall collapsed and retreated backward. That's the reason why it's called retrogressive. As a consequence of warming temperature, there were slumps newly formed every year, and the old ones also expanding. So the objective of this research is to construct a multi-annual inventory of the slumps, and we attempt to use the image and the corresponding labels in one single year that we called the source domain, and transferred this trained model directly into the other years that we call the target domains. But challenging is that those domains share different contextual information, like the colors. And we can also see the apparent discontinuity due to the mosaic between the image tiles. So we apply different domain adaptation approach. To save time, I only introduced one, the psychogenerative adversarial network. So this is an illustrative example on how it's going to look like. So it can keep the shape of the target, like this horse, but fill in the brown color with the zebra stripes. When we apply this approach in our study area, in the synthesized image, it can keep the shape of the slums of those from the target domain, but retouched image with the style transfer from the source domain. So this approach can effectively improve the accuracy of our segmentation. In a course of 4 years from 2019, the number of slums increased by 10% and the area increased by 35%. And next, we are going to ask, what are the hydrodynamic forces in regulating the slum's development? So definitely the temperature, right? And also the precipitation. Then we apply this conditional correlation analysis by consider the Kendall's tau B coefficient. We found that when the land surface temperature is below 0 Celsius degree, as denoted by the blue boxes, the faster subsidence, that is the lower part of this y-axis, is associated with lower precipitation, that is a drier climate. While when the land surface temperature is larger than 0 Celsius degree, denoted by the red background, we can see the faster subsidence is associated with higher precipitation, that is a wetter climate. So that is to say, the relationship between subsidence and precipitation can be completely reverted depending on the land surface temperature. Okay, so lastly is about the chronic hazard. Let's start with the slow-moving landslides. Before we start, let's look at this picture of stew called the slum volume. Basically, it's a mixture of veggies and noodles as well as meat. It is also called a type of meal to clean out the fridge. And study site is a translational Earth slide of the same name in southwestern Colorado. From this picture, we can see it's indeed a mixture of different colors and grain size of the soils, salt rocks. And this landslide is credited as an ideal natural laboratory because it moves as fast as a couple of centimeters per day, and that amounts to 7 meters per year. And this strong signal has persisted for the past 300 years since its reactivation. It travels like a snake downhill by 4 kilometers. So here we applied airborne UAV SAR data collected from 4 independent flight lines. So note that although we have UAV in SNAM, we do have pilot and technicians for each flight mission. And we also have the satellite Sentinel-1 imagery from the ascending and descending tracks. And we applied the hybrid InSAR and pixel flight tracking method to generate more than 1,000 pairs of displacement maps, which are 2 orders of magnitude larger than previous studies. And we also have in situ geodetic and hydroclimate data. So here, the first attempt of this study is to refine the landslide margins, and we add a new element, kinetic element over the heads, marked by the red line here. So this can be easily extracted from the contrast between the white means no motion and reddish means appreciable motion from the line of sight velocity map. Well, we also notice this lobe over the head shows a opposite sign compared to the remaining part of landslides. And this is because this part is moving against a curved flank. Say for the ascending results, this lobe is moving away from the sensor, where the majority of the landslides is moving downhill towards the sensor. Well, the middle part moves too fast, and it exits the resolvability of INSAR when we apply in the Sentinel-1 imagery. Well, the lower part, we can see distinct colors. And this is because the northern tip of the toe occurred on a local inclined slope. So the direction and magnitude of the motion is different from the adjacent kinematic element. So here the hybrid INSAR pixel tracking results shows the horizontal rotation over the head. When we compare with the landslide margins mapped in the field survey in 1991 by USGS scientists and their Italian collaborators, we can see this slip vectors has existed beyond this point. So it's moved downhill by more than 14 meters. Well, the time series displacement agree well with 3 extensometers installed at the lateral shear surface. And then we extracted the longitudinal velocity, that is, we project the 3-dimensional displacement into this dotted line. And we can see the narrowest hooper and neck of landslide shows the largest rate by 14 millimeter per day. And somehow the landslide velocity is controlled by its rheology, and we have 2 pieces of evidence. The first one comes from the toe. So here we compare the edge of the toe from the field survey in 1991 and 2 sets of LiDAR DM collected in 2015 and 2019, as well as our field survey by using the portable GPS sensor in this past May. So here we can clearly see the toe keeps advancing and pushing and destroying any disturbance in front of it. So this immediately reminds us about Newtonian flow. And this is the picture I took this morning from my apartment. This is the most accessible non-Newtonian material that we can find in our daily life. That is the toothpaste. And the second piece of evidence comes from the inclinometer survey. So inclinometers can measure the internal shear deformation referring to the sensor at the bottom. So we can see in the shallow 5 meters depth, there are negligible displacement. And between 5 to 10 meters depth, that is about 20 millimeter. But during this 40-day survey, the surface displaced by as much as 600 millimeter. That is to say, the large displacement we observed at the surface mostly comes from the lower ear zone. There's another suggestion for the non-Newtonian flow. And this equation generates a stress condition. The tau C is ear stress at the ear surface. In the most classic Bingham model, the power law index n equals 1 and tau C is a constant, but there will be no flow region at sites. But from our extensometers and also SAR transects, they both reveal the appreciable displacement when it's even really approached to the site. So we are up to the power law model, where above is a pseudo clock and is gradually changing to the ear zone below. But in light of the 2D dislocation model, we come up with a new description for the slope channel. So basically, it's the superposition of 2 mirrored arctangent functions. So include the 3 critical geometric parameters: the depth at the central axis, the stiffness between the basal and the lateral shear surface, and the tilt of the basal bed. So here we allow for asymmetry. Then considering the Gamma equation and boundary condition of no slip at base and no stress at surface, we end up with this analytical solution for the longitudinal velocity. And we separate out the 3 groups of parameters. These green ones are known, like Ux is the longitudinal rate, and we can obtain a surface rate from SAR. And rho density and alpha is the slope angle. And the reddish ones are relating to the geometric, relating to the rheological parameters, K and M. And blue ones relates to the channel geometry. And then from the uphill projection of the stable offslide area, we can simulate the basal surface for the distal part of the toe. That is for the last 2 profiles. So we can resolve the power law coefficients, that is rheological coefficients, K and N. Assuming that the landslide material share the same characteristic rheology, we can further constrain the slope channel for all the remaining profiles uphill. So here's an example. The brown curve shows the basal surface channels, and the black and underlying gray lines shows the longitudinal velocity from SAR observation and our model. Since now we have got all these parameters, we can run the forward model to get the longitudinal rate at any given depth. So here the horizontal axis denotes the magnitude, and color shows the vertical gradient. So the bottom, when it's attached to the base, there will be 0 velocity, but largest rate in color, in the reddish color. But in the shallow part, there will be already the largest rate, but the negligible change in the vertical direction, so it's in blue color. And this diagram summarizes the geometric parameters from the head to the toe. The gray line shows the depth. In the narrow neck of the landslide, it has the largest landslide depth by up to 25 meters. And orange line shows the tilt of the basal bed. So we can see in the big band zone of stretching between the head and neck, it shows abrupt increase. That means increase the asymmetry in the slope channel. And this diagram illustrates the basal geometry, so we can infer the landslide volume. Okay, the last case is another alarming chronic natural hazards relates to the climate change. We know that most of coastal cities were built on top of the reclaimed land that is naturally subjected to the consolidation settlement. So the landward side is moving downward. On the other side, the sea levels are mostly rising. So these 2 parts are moving at a similar rate, but towards the different directions. So that is to say, somehow the relative sea level rise, referring to the sinking land surface, will be amplified than that we consider the sea level rise alone. So we started this research from the Miami suburbs area, but today I'd like to just show you a more recent study in the Bohai economic rim that is also called the coastal gateway of northern China. So this area encompassed the Hai River, that is the one flooded in 2023, and Yellow River estuaries, and there have been intensive industrial production like groundwater extraction, oil gas extraction, and coal mining. Somehow here we use Sentinel-1 to extract the regional surface displacement. Actually, the land subsidence will be more severe in decades ago, since the implementation of the South-to-North Water Division program run by the government. The groundwater pumping has been much lessened. So here, when we compare the background color, that is subsidence, with those circles, which denotes the groundwater level changes, we can see the mild surface uplift coincide with those groundwater stations with increased water height. The time series displacement from INSAR agree well with GNSS observations with standard deviation less than 1 millimeter per year. We also know that the natural consolidation settlement is decelerating process due to the gradual dissipation of the pore pressures. So we introduce an exponential equation to characterize this decaying process. By integrating the time-dependent rate changes with time, we can derive the cumulative displacement and thus refine the position of the elevation, the surface elevation in any given future years. And then we incorporate the projection of sea level rise from the IPCC, and we also consider different land covers. Because the seawater overflow will encounter different friction depending on the land cover types. So here's a schematic view about the flood water extent in 2050, 100, and 150. More importantly, in this study, we quantify the role of land subsidence in coastal inundation. Taken the year 2100 as an example. So this figure shows the inundated area in different climate change scenarios, the affected population, and the water depth. And the first row shows the results with the consideration of land subsidence, and the second row shows that without land subsidence. Well, statistically from this table, we can see the land subsidence can increase the inundated area by 260%. We also increase the affected population by 385%. And lastly, I'd like to conclude my talk today by quoting a traditional theory in Chinese medicine, 慢急分治. That is to treat acute and chronic conditions separately, especially amid the climate change crisis. We do believe it's time to set up the tailored mitigation goals to maximize sustainability and resilience. With that, I'd like to stop and open for questions. Thank you.
Thank you, Xie, for a really great talk. It was really interesting seeing kind of all the different aspects of the research your group is doing. And yeah, the analogy to kind of human health is really a nice way of framing it. I'm just going to remind everyone that, so we have the Q&A panel at the top, so you can put your questions in there, and we will get to them. I think you should be able to see the questions in there when they appear as well, but I'll read them out just so everyone knows. While we wait for people to have some questions, I can start off with one. So for the flooding example that you showed at the beginning, at the moment you're using mainly SAR data for that, with Sentinel and was it GOFEN, which I think is also C-band. Have you thought about using kind of different wavelengths or adding optical data into it as well? How that would act, like, would that help with the modeling and applying it elsewhere?
Yes, thank you for the question. So here, in terms of different wavelengths of SAR data, I think here the optical images will be more helpful. I skipped that section, but actually it is not realistic to capture all the floods, the maximum flood areas by just relying on the SAR imageries, right? So we note that for the areas that has been flooded, even though when the flood recedes, the moisture is still maintained at the high levels. So we can actually use the NDWI or the NDMI, the moisture or the wet index, the water index from the optical scenes to recover the maximum extent of the flood water.
That's really cool. I think everyone's very shy this morning for some reason. which
Morning time.
Yeah. With just because you had that slide on, are you just using the single polarization or are you using the dual as well? Because I guess that makes quite a difference with the SAR data if you're using that.
Yes, we actually use all the polarization. So here we fit in the data with this like VV, VH, and their ratio. And similarly for the Galvin 3, we apply HH, HV, and their ratios as 3 independent bands and fit them into the DeepLab V3 algorithm. So you may notice that those imagery are operated with different polarization. So definitely there will be some like a systematic shift between the VV and HH, although they are both single polarization at this point. So we applied the histogram matching. That is a really neat procedure to standardize our input. So that's the reason why by just add this pre-processing step, we can somehow generalize this approach for SAR imageries with different polarization.
Yeah, that makes sense. We have a question actually. So this is from Manny. He says, "Thank you for your presentation. I would like to ask you about what approach would be useful for sudden glacier movements. Have you had a chance to think about glaciers and I guess how they move? Because I guess they're melting and like the deformation across them."
Yes, for the glacier, I think we have to use the peaks of that tracking. So the good thing is that, okay, so pixel tracking can be applied to the not only SAR imagery but also optical scenes. If the weather is clear, usually the optical remote sensing scenes will have a better spatial resolution. And recently, I also noticed that this is a part of the ongoing research. The hue shade map from DEM can be also used as the source of data for the pixel flight tracking. And it's really powerful, especially if we have high resolution DEM like the LiDAR span different time. That's what we implemented in the Slumgullion landslides.
I guess for quite big motions, you need different methods to do that. Yes. We have a question from Karen here, which is, how are the government and local authorities using model data to mitigate these climate hazards? And also, great talk.
Sorry, I didn't hear the first question.
So how are the government and local authorities using the model data to mitigate climate hazards? It's quite a big question, I guess.
Yes. So, okay, the good thing, for now is that for those emergent events like floods and earthquakes, the government will release those Chinese satellite imageries for free, and also some supplementary data set. Just try to bring in all the scientists to give some mitigation measures. So I think this is something that we've been seeing in these years, like these imageries will be publicly available, but just specifically for the event.
I guess, when they publish it, do they then also, I guess, have the communication about what you see in the images and kind of your understanding of what's happening? Is that kind of I guess it's a two-way discussion then.
So usually there will be an association to host some engineering, earthquake engineering groups worldwide. They will assemble all the resources to generate a report just within a couple of days spanning the event. So that is also something happened here. But this is in the name of the association.
Yeah, okay. We have one question here, which is how are you integrating and validating the SAR data with the UAV? Yes, because you've used LiDAR and airborne, I guess.
Oh, okay. I think that is.
I think that's what this question means.
UAV SAR. I think that means the UAV SAR. So here, first we have UAV SAR image from 4 independent flight lines, and we also incorporate with another 2 perspectives from the symptom, the satellite imagery, and we can generate the spatial temporal displacement. In terms of the validation, okay, here we compare it with the field survey from extensometers that is denoted by this gray symbols, and they show very somehow good consistency in terms of time series. If time series are consistent, then let alone the rate, right?
Yeah. Awesome. I guess if no one else has any questions, oh, there's another question. So this is from Manny again, which is, what do you think about glacier lake outbursts? Is there any way we can monitor these?
It's an interesting topic, and it's also something we probably will start working on. At least now we have our collaborators. I think now we need to try to leverage all the remote sensing imageries, not only in the optical and also the SAR, because they're really supplementary to each other on the weather conditions, on the accuracy, and also the temporal resolution. And once we got the displacement, we can just infer the geometry, the subsurface geometry of the mobile mass. And then there are a lot of empirical model to infer, okay, once this mobile mass being collapsed, then what will the run out distance be, and in which region, and then we can use this information for the mitigation in the downstream area.
Yeah, as you say, the combination of the data sets, there's so much information in both of them.
Yes.
Yeah. I think we can wrap it up there. Thank you again for an amazing talk. I think I really enjoyed it. I hope everyone else did as well. And thanks for everyone who asked questions. So just a reminder, we've got a webinar scheduled for the mid-September, which will be on modeling magma mush reservoirs, so quite different from this one, but I encourage everyone still to come along, and we'll be sharing that information a bit closer to the session. So yeah, thank you again, and have a good rest of the day, evening, morning, wherever you are.
Yeah, thank you, Edna, and thank you everyone for attending.